In this video, we're going to be looking at three different types of KEQ calculations, starting with the most straightforward example, the calculation of the value of KEQ itself. In any case, the first thing to do is always write out the KEQ expression based on the equilibrium equation that we're given. So since there's only one product, we would write concentration of nitrogen dioxide, and we know the stoichiometry coefficient of 2 becomes a squared exponent, which also applies to our first reaction, concentration of nitrogen monoxide, and the stoichiometry coefficient of 2 becomes a squared exponent, and then we take this and multiply by concentration of our last reactant, oxygen gas. Now, the first problem that is going to occur is a misreading of units if you're not careful. So remember that KEQ expressions are always a ratio of concentrations, but we see that our initial measurements of each of the reactants and products is only given in moles. So let's go ahead and divide the number of moles by the volume of the container in order to find the concentration of each gas. So 6 moles of nitrogen dioxide divided by 2 liters comes to 3.0 moles per liter of nitrogen dioxide, taking 2 significant digits into account. 3 moles of nitrogen monoxide divided by 2 liters comes to 1.5 moles per liter, and 0.2 moles of oxygen gas divided by 2 comes to 0.10 moles per liter, and now all we need to do is take these concentrations and substitute them into our KEQ formula. So that would be 3 moles per liter of nitrogen dioxide squared divided by 1.5 moles per liter of nitrogen monoxide squared times 0.10 moles per liter of oxygen gas. And if you put this into your calculator, this comes to exactly 40. And again, because we're dividing concentration by concentration, KEQ has no units because the concentrations cancel each other out. However, we can see, as with the next problem, calculating KEQ is not necessarily always this straightforward. So we're told that 4.00 moles of nitrogen dioxide is added to a 2-liter reaction flask. Now let's go ahead and convert this into a concentration. So 4.00 moles divided by 2 liters is 2.00 moles per liter of nitrogen dioxide, and allowed to equilibrate. And at equilibrium, 0.500 moles of nitrogen monoxide is found. Again, we can convert this into moles per liter. 0.5 divided by 2 is 0.250 moles per liter of NO2. Now, if we check the wording, we see that something is not quite right with these measurements here. If we consider when KEQ occurs, when the concentration of products and the concentration of reactants is constant, we know that this only occurs at equilibrium, but we see that if this nitrogen dioxide is put into the reaction flask and allowed to equilibrate, that means that this measurement here is not at equilibrium. This occurs in our initial phase before the equilibrium has been reached. So the question is, how do we find all of the missing measurements? Well, that's where we can consult a Rice table, keeping in mind when these measurements occur that the concentration of nitrogen monoxide occurs at equilibrium, so we can write 0.250 moles per liter in here, but the 2 moles per liter of nitrogen dioxide occurs before the equilibrium is reached, so we would write this in here. Now, we're not told anything else about our initial conditions, so allowed to equilibrate means that this nitrogen dioxide is going to decompose, so only the reverse reaction is going to happen because we have no initial quantity of our reactants, which means our equilibrium is going to shift to the reactants. Now, what about the change? Well, we know that the change that occurs is based on the stoichiometric ratios, because this is the only time when these ratios occur. So that means that because there's a coefficient of 2, we don't know what this magnitude is, but we can say that because oxygen has a coefficient of 1, it is going to gain a concentration to a magnitude of X, and because the stoichiometric ratios of the other reactants and products are 2, the change is going to be double that. So plus 2X in the case of nitrogen monoxide because the equilibrium is shifting to the reactants, and minus 2X because it's shifting away from the products. And therefore, if we calculate what X is, we can find what our 2 missing measurements are. And fortunately, we are given one of these quantities at equilibrium, so we're told that 0.250 moles per liter, which is our equilibrium quantity of nitrogen monoxide, must be equal to 2X based on how the equilibrium worked, meaning that X must be equal to 0.125 moles per liter, and now that means we have also found the concentration of oxygen gas at equilibrium, and the calculation to find the concentration of nitrogen monoxide is relatively straightforward. So if we know that the concentration of nitrogen dioxide at equilibrium is equal to our initial concentration minus 2X, and we know what 2X is already, we can find that this is equal to 1.75 moles per liter, and now that means we have all of our equilibrium concentrations, which means that we can calculate KEQ in exactly the same way. So concentration of nitrogen dioxide squared, so 1.75 squared, divided by the concentration of nitrogen monoxide squared, so 0.250 squared, times the concentration of oxygen gas, which would be 0.125. And if you put this into your calculator, this comes to exactly 392, again with no units because the concentration unit cancels each other out. Now, in the final situation, we are calculating this time an unknown initial concentration if we are given KEQ, so the calculations work a little bit differently. So here we're told an unknown quantity of nitrogen dioxide gas is added to the reaction flask, and we're not told anything else about our initial conditions. So again, we don't know what this quantity here is, so we're just going to call it a question mark here, but we are told through an absence of information that there are no reactants present, which means the equilibrium shift is going to move from the products to the reactants, meaning that this initial concentration of nitrogen dioxide is going to decrease. Now, because we know the direction of the equilibrium shift and because we know about the stoichiometry coefficients, we can write in the changes here. So we know because of the stoichiometry coefficient of 2, we're going to have a change of positive 2X for nitrogen monoxide and positive X for oxygen gas, with a change of minus 2X for our nitrogen dioxide, meaning that the best we can do at equilibrium is our unknown initial concentration minus 2X. Now, the question also gives us at equilibrium, the final concentration of nitrogen monoxide was found to be 0.8 moles per liter. So we can go ahead and write that in here. And because we know that 0.800 moles per liter must be equal to 2X, we have just figured out that X must be 0.400, which means that we have also found the equilibrium concentration of oxygen gas like this, and we've also found what we need to subtract our unknown initial concentration by in order to find it. Now here, because we're not solving for KEQ, the actual algebra to solve this works a little bit differently, but the setup works exactly the same. So we have our KEQ expression, which is concentration of nitrogen dioxide squared divided by concentration of nitrogen monoxide squared times the concentration of oxygen gas. But this time we're going to be putting in one of these concentrations that contains an unknown here. This is what we want to solve for. So we know the equilibrium concentration of nitrogen dioxide is going to be our unknown initial concentration minus 2x, which is 0.800 moles per liter, and the rest of our values we can put in exactly the same way. So concentration of nitrogen monoxide is 0.800 squared times the concentration of oxygen gas, and this time we know what KEQ is because the question gives it to us. We know that KEQ is equal to, let's write that more clearly, 24. So now all we need to do is rewrite this equation such that our unknown is isolated. So here we're going to move everything in the denominator to the other side by multiplying by both sides, and to get rid of the squared exponent, we can take the square root of both sides once that's done. So if we rewrite our expression, we would have our unknown initial quantity minus the 2x value, 0.800, is equal to the square root, to again remove the exponent here, the square root of 24 times the concentrations of our reactants here. And then finally, the last step is simply to isolate what this unknown quantity is, which means that we can add the 2x value here to both sides. So if we simply do plus 0.800 to both sides, that would mean that our expression turns out to be something like this. And if you take the time to put all of this into your calculator, we can find that our unknown initial concentration comes to approximately, because there's a square root, so the decimal is going to get messy, approximately 3.28 moles per liter of nitrogen dioxide. Now, the lazy among you or the inobservant among you will just assume, okay, we found this unknown, we're done. But we need to be careful about the question, because the question asked us to calculate the unknown number of moles of nitrogen dioxide that got added. So we have one trivial calculation here. We need to convert our concentration into moles. So we simply take our original concentration and multiply it by the volume of the container, which in this case is 5.00 liters. And if you do this, your calculator should read approximately 16.4 moles of nitrogen dioxide were added here. In the next part of this KEQ calculations video, we're going to look at more complex calculations where we know what KEQ is, and this time we're looking for unknown quantities that occur at the equilibrium stage based on how the equilibrium is going to shift.